Chapter 7 addresses electrochemistry, and electrochemistry is a union of Gibbs free energy, electron flow, and chemical transformation. And study of the union between chemistry and electricity, driven by free energy release, has provided a rich history of remarkable discoveries throughout the history of science. But electrochemistry has experienced a dramatic rebirth in just the last 5 years or so. And that rebirth has been propelled by the emergence of energy production and storage requirements as a dominant problem confronting both science and public policy. And a key part of why this rebirth of electrochemistry has taken place has sparked, if you will, by efforts to advance key technologies associated with global demands for energy. And one aspect that should be mentioned is that electrochemistry also unifies all of the ideas that we developed in chapters 1 through 6, and it brings all of these together in a remarkably unified way. So a key driver behind the remarkable emergence of electrochemistry into a leading topic of advanced research internationally has been the rapid onset of irreversible changes to the climate system. Now, we've already discussed this irreversible rapid loss of permanent Arctic ice, in which the feedbacks are driving the system more and more rapidly toward this condition of zero floating ice in the Arctic. So the more ice is removed, the more rapid is the removal of subsequent ice. But also, 2017 was a remarkable year, and if we can look at the United States in particular, about $320 billion of losses occurred. And these losses occurred in storm systems through the Midwest, in wildfires throughout the West, both Southwest and Northwest, by drought conditions in the Midwest, and by a series of hurricanes that reached the southern extremity of the United States. But this issue of drought is related directly to this question of the loss of Arctic ice, because as ice disappears from the Arctic warms more rapidly than the rest of the globe. That diminishes the temperature difference between the equator and the pole, and that tends to shift the jet stream northward. And that tends to pull the climate of northern Mexico into the central southern part of the United States. And the recurring drought is a result, in part, of this effect. But also the drought is driving the southwest fire threat. And the remarkable thing about the southwest is that the vegetation there is highly arid, and when that vegetation is burned out, it doesn't replenish itself. In the case of the northwest, because there's less of drought conditions there, even though it induces fire, the regrowth in the northwest is far more probable than regrowth in the southwest. So these aspects are driving the recognition of how rapidly the climate is changing and raising the level of necessity for electrochemistry to provide global energy. And one of the things to focus on here is the irreversibility associated with the flow of heat into these subsystems of the climate. And that's what thermodynamics tells us so clearly, that, for example, the Antarctic glaciers are disappearing very rapidly, but there's nothing to reform them. The same thing with Greenland. The glacial systems of Greenland are beginning to lose ice mass very, very quickly. And the important aspect of that is sea level rise. If we take a map of the United States currently, and let's just focus on Florida. If we add just 3 meters of sea level rise, for example, the Greenland glacial system contains 7 meters of sea level rise, the Antarctic contains 70 meters of sea level rise if that ice were to melt. But if we add just 3 meters, a large part of the entire peninsula of Florida goes underwater, because the Florida peninsula is very, very close to sea level. So the issue of sea level rise becomes very important, and I've picked just one example. All coastal regions are affected by even a fraction of a meter increase in sea level rise. At the same time, we're also looking at remarkable innovative advances many of them based on electrochemistry. And we can pick out, for example, the electric automobile and the rapid inclusion of electric automobiles into the transportation systems. And one of the aspects about electric automobiles is when you drive one, you realize how much more fun and how much better they are than a gasoline car, because an electric motor derives maximum torque at 0 RPM, so these cars are very quick, very quiet, very smooth, and very enjoyable to drive. The next developments involve very high-speed rail services, all electrified. And these trains now compete in velocity with aircraft, typically half the velocity of the aircraft, but they don't have landing, takeoff problems, and many aspects make rail transport for intermediate distances extremely efficient. Then there's the issue of battery technology. And battery technology is one of the most fascinating applications of electrochemistry, because there are huge steps being made in increasing the energy content per kilogram of batteries. And this plays directly into the range that we can realize from electric automobiles. Another example is energy storage. Flow batteries involve a whole new chemistry where the anode and cathode of that energy storage is fed by very large, typically underground tanks, and it massively increases the capacity of energy storage in these battery systems. So electrochemistry tells us a great deal about the pathways, the technical pathways into the future. But electrochemistry is very powerful for unifying ideas because, for example, if I take an electrochemical cell, that electrochemical cell converts chemical potential, that is, a release of Gibbs free energy, to a voltage. That voltage drives an electric motor through an electrical potential. That motor can do work, for example, raising a mass, and that is related directly and quantitatively to gravitational potential. And it turns out that a huge amount of information was garnered by Michael Faraday, who was the father of electrochemistry, but also the father of electromagnetic induction, which is incredibly important for the electric motor. And so it was the recognition that electrochemical energy converted to electrical energy to do work allowed a relationship between a change in Gibbs free energy and the voltage of the cell, a direct connection, because it turns out that delta G is the maximum amount of work that can be extracted from a chemical reaction. So the very basis of electrochemistry came out of the coupling of an electrochemical cell to an electric motor, and this was in the latter stages of the 19th century. So when we focus then about what electrochemistry actually contributes to society, let's take a Tesla Model S. This is a large sedan. It'll hold 5 adults and 2 kids in jump seats in the back, so up to 7 individuals. So it's a large automobile. And there are a lot of different comparisons we can make. If we use the energy unit of kilowatt hours and look at how many kilowatt hours are required to drive 100 kilometers, it turns out that for an average automobile that gets 20 miles per gallon, it's about 125 kilowatt hours per 100 kilometers. If we're sitting in an SUV and stop-and-go traffic, we get about 10 miles to the gallon, and that converts into 250 kilowatt hours per 100 kilometers. Now, if we drive a hybrid, that drops all the way down to 62 kilowatt hours per 100 kilometers, or a Tesla Model S drops us down to 15 kilowatt hours per 100 kilometers. This is a direct reflection of how efficient an electric motor is. It converts 95% of the chemical energy to motive force rather than 15%, which is typical of a gas engine, as thermodynamics has taught us. But let's look at the financial impact. And this depends on the price of gasoline, of course. But if I compare what's spent in the United States to drive the 20,000 kilometers per year that an average car in the United States drives, That costs about $600 billion a year for gas at $4 a gallon. If I'm driving a Tesla Model S, I drive the same 20,000 kilometers, and the total cost for all individuals in the United States to do that is $72 billion. So if in the United States tomorrow everybody switched from fossil fuel-based driven automobiles to electrical automobiles, we would save on the order of a few $100 billion a year. This is a very important economic consideration that comes directly from electrochemistry. But now we recognize what electrochemistry can do in terms of generating solar power, wind power, geothermal, and other renewables, and the fact that all residential, commercial, industrial, and transportation sectors use electricity with one exception, and that's aircraft. But aircraft consume only about 4% of the total energy, which can be generated by biomass. So on an economy that's based on electrochemistry through renewable energy, 90% of that energy is useful and only 10% is waste. That is in sharp contrast to the Lawrence Livermore National Lab flowchart that we've looked at before, where 67% of the primary energy from fossil fuel is wasted, 33% is useful energy. And not only that, this shift through electrochemistry to coupling electrical output to all aspects of the economic need terminates the release of CO2 and methane to the atmosphere. So electrochemistry is the key to the future.